Hello, it's Mr. Allred again. I'm going to continue talking about Riemann sums. If you remember from the last video, we were trying to calculate the area under a curve. And we looked at making several rectangles to estimate that. So you went through some lessons with sigma notation, and basically what we have here is an I which runs from 1 to n. That would be the number of rectangles, just to review here. F of x is the height of those rectangles. So you would pick an x value, whether it's the left side, the right side, the middle, the midpoint. Plug it in. That would give you a y, which would be the height of that rectangle at a point. And this over here, this change of x, this is basically a width, how wide the rectangle is from one x value to the next. Just trying to put this in a cleaner notation for where we're moving. Like we said, what we primarily worked with, or I asked you to look at, were left and right Riemann sums, which is measuring the height of that rectangle either from the left endpoint or the right. But if you went through some of the other videos on Khan Academy, you would have seen some variations and some other options. Okay, so let's travel down this road together. So what we're trying to do is we're trying to get the most accurate area we can under a curve. So some of the examples in previous videos, instead of a curve, we might have a straight line, and that would allow us to break the shape under here into rectangles or triangles or trapezoids. But when it's curved, when it's not straight, then we don't have that luxury. So we did use the idea of rectangles to estimate it. So right here, if you look at the light shaded, these are right Riemann sums in the first graph, because they've got the height on the right hand side. And this first one, curve, is done using two rectangles. And you can see a lot of space on the outside here. So let's just look at the light ones all the way through. The second graph, we used four rectangles, which gives us a little bit better estimate of what the height of that rectangle would be at a time. So over here, this one looks kind of far off, but depending on how the curve is changing, it looks like there's less discrepancy here above that curve. That's kind of an overestimate or a waste. And then down here, let's see, this looks like 8 rectangles. And we see very little waste or overestimate above the curve. So what we're trying to do, or what these graphs are intended to show, is that we're estimating the area of a curve right here. And the more rectangles we used, the better that estimate would be, the more precise we could get it down to. So this goes down to 8, but if we can use any number we want. I'm just going to stay with multiples of 2 here. So if we cut all of these in half, we'd have 16 rectangles, which would be even a better estimate. But the idea is, even though more rectangles create a better estimate, it becomes more work and it becomes impractical after a while, especially since it's just an estimate. So let's see what we can do down here. So what would be ideal? How many rectangles would we want? Well, to truly answer that question, we'd say we want an infinite number of rectangles. And if we could make an infinite number of rectangles between two endpoints, then they'd almost be like lines or just slices. You could think of it that way. So it would just be the height everywhere across that curve. So the width here, now we've got the same summation formula over here in the sigma notation, but because I want an infinite number of rectangles, I need them very, very thin. So going back up here, the more rectangles I used, the thinner they got. Okay, so to get a better estimate, we want more rectangles, which means they would be thinner. So we're letting that width, the change in x, approach 0. So they're infinitely thin. Okay, so there is the width, and we still got the same height. That means that basically n is going to be infinite, okay? Because if we take no matter how big of a space and we make the pieces within that space really, really thin, we're just increasing the number of them. So since they're infinitely thin, like little slices or slivers or almost like peeling a page off a book, we're getting more and more of them. Okay, so basically what we're trying to say here is we would like as many rectangles as possible. That would be an infinite number, and if we want to talk about that, we would make them almost zero width, so there'd be many of them. Okay, so that's where the limit comes back into play. Okay, so let's see here. Oh, end of video. We will continue in a moment.